quite some time, so I was very excited when I got the invitation to come. Also, I've not given a Blackboard talk in quite some time due to the pandemic, so I wanted to take the opportunity to do so now that I finally am giving a talk in person. So I hope you won't mind this somewhat analog talk. So today I want to tell you about quantum field theories in low dimension, with low central charge, and with few primary operators. So essentially, all those adjectives I threw in make the theory more or less as simple as it possibly could be. And many exact results are possible in this setting. But I hope to convince you that there's still a lot more to be discovered and a lot more to learn even in this relatively simple arena. And just to give you some sense for where this talk is going, let me flash the main result that I'll be working towards in advance, and then we'll build it up in stages. So this is a result in a recent paper of mine with Sunil Mukhi. And essentially, it's a result about classification. And what it says is that every, by the way, if these words at the moment are somewhat mysterious, don't worry, I will explain them in due course. But the result is that every 2D unitary compact rational conformal field theory, V, with central charge less than 25 and with two multiplets of primary operators is either one of these four WZW models at level 1 based off of the Lie algebras SU2, G2, F4, or E7, or it is a coset of the form A mod V, where V is again one of these theories up here. So I'm calling them MMS for Madhur Mukhi Sen, who originally studied them. And A here is going to be a meromorphic conformal field theory with central charge 16 or 24, where the adjective meromorphic here means that it has exactly one primary operator, the identity. And as I will explain momentarily, the numerators are classified. Theories A with C equals 16 or 24, which are meromorphic, have been classified. So in particular, we get a very explicit problem that we can go out and try and solve, which is enumerating all the inequivalent cosets of this form. And when you do this, what you find is 123 theories in total, with most of them being new. So this is the main result that I'm going to build up to. But before we get there, let me start with some motivation. I'm sure I don't need to say what I'm about to say for this audience, but I find it helpful in talks to remind myself why I'm giving the talk in the first place. So there's many reasons you might want to study rational conformal field theory in 2 dimensions. So the first is, of course, that 2-dimensional physics is very tractable, and many exact results are possible. And in particular, we hope that the lessons that we learn in 2 dimensions will generalize to more general settings, at least qualitatively. The second is that CFTs are fixed points of renormalization group flow. And so in particular, what this means is that they are answers to questions of the form, what is the low energy physics of model X? And this is a question that we very often ask as quantum field theorists. Another motivation comes from statistical mechanics. Where due to universality, systems near their phase transition points are described in the continuum by conformal field theory. So their second order phase transition There's a CFT description. In particular, the sort of microscopic details of the system are washed out, and what's left is only long wavelength physics, which is accurately captured by a CFT, where, again, a lot of observables are exactly calculable. So that was motivation for condensed matter physicists. If you're a high-energy physicist, then you probably care about two-dimensional conformal field theories because they describe the world sheet of string theories. Another relationship to gravity is via ADS CFT. So by the ADS CFT correspondence or holography, 2D conformal field theories are related to gravity in 3 dimensions. So now, of course, if you're interested in realistic models of gravity, then the regime that you're interested in is very irrational theories at very large central charge. So in particular, that's a diametrically opposite regime to the one I'm considering. But actually, recently there have been various toy models of the ADS CFT correspondence that have been studied, which in particular use ingredients that are more like these simpler rational conformal field theories of low central charge. So there may be hope for using some of the theories that I mentioned in such settings. If you don't like low dimensions, it's okay because oftentimes chiral algebras or vertex operator algebras or 2D rational conformal field theories are the right algebraic object to encode protected physics in higher dimensional supersymmetric quantum field theories. So it's 2D chiral algebras. Code protected observables in higher D CZ CFTs. A very beautiful example of this is 4-dimensional superconformal field theories with 8 real supercharges. They have a protected sector, which is described by chiral algebra. Now, unfortunately, this chiral algebra is non-unitary. So again, we're in a different regime than the one that I'm probing. But I think there's still hope that some of the technology that I'll tell you about today could be generalized suitably to be able to say something about theories like this. And the last motivation comes from pure mathematics. A very famous example, and in some sense, one of the reasons why vertex operator algebras were invented was monstrous moonshine. So in that context, 2-dimensional rational conformal field theory was the right explanation for, at the time, mysterious connections between exceptional finite group theory and number theory. And so these are just buzzwords at the moment, but another place where chiral algebra show up is, of course, the lineage correspondence. Okay, so I think that's enough motivation. So let's delve a little bit in. So let me try to summarize the current sort of state of the art for what we know about classification of 2-dimensional conformal field theories. So of course, classifying 2D conformal field theories without adding any extra adjectives is I think it's safe to say, probably impossible problem, at least not explicitly. So you have to introduce some further qualifiers to make the problem more tractable. So in particular, it's very natural to organize the classification by the central charge C. So I won't define this for you here because if you haven't seen it, then I don't think the definition will be very helpful. But let me just say that it is the most important quantity associated with the CFT, and it appears all over the place. I'll give 3 examples. It characterizes entanglement entropy in the vacuum. It characterizes the asymptotic density of states at high energy. By something called the Carty formula. So the high energy density of states is a completely universal quantity that only depends on C. And it's also what's known as an RG monotone. So if I imagine starting with a UV CFT, deforming by some relevant operator, and flowing down to IR, and I compare the central charge of the UV to the central charge of the IR, what you'll find is that the central charge always decreases. So in particular, if you're interested in questions like what is the low energy IR fixed point of some UV CFT, it can be very useful to have answers to questions like what are all theories with central charge less than C? So that gives you a menu of the possibilities that this IR CFT can be. So that's another reason why it's very natural to organize the classification by central charge. Okay, so let's see how far we can get with just with this as our only qualifier. So because I'm focusing on unitary theories, that implies that C has to be greater than 0, greater than or equal to 0. And so C less than 0 is excluded. C equals 0 corresponds to boring theories from the point of view of conformal field theory. They're gap theories, like topological theories. And then famously, between central charge 0 and 1, there's discretely many theories that accumulate to 1. And they're all so famous that most of them are given names, at least the low-lying ones. There's Ising, there's tricritical Ising, so on and so forth. And they occur at central charge 1 minus 6 over m plus 2 plus 3. So these models here are known as the minimal models. And at each of these admissible central charges, there's only finitely many theories, and they're completely known and classified. So that completes the entire classification from C equals 0 to C equals 1. Those are all rational theories. At C equals 1, let's zoom into what happens there. Something somewhat drastic happens. An entire conformal manifold opens up. There's a continuous moduli space of theories, which I will draw for you. So one of the branches of moduli space is labeled by an integer r, and you can think of these theories as compact free boson theories. So if you're a string theorist, and then to you, these models are what you get when you compactify spacetime in one of the dimensions on a circle. You get a continuous family of theories that are labeled by the the radius of that target space circle. In principle, you might have thought that this is 0 here, but actually 0 is over here. This is square root of 2. And the reason we only go down to square root of 2 is because there's a famous duality called T-duality, which relates the theories with r greater than or equal to square root of 2 to those with r less than square root of 2. So T-duality acts as the second branch is obtained from this branch by gauging a Z2 symmetry of this branch. So it's called an orbifold usually. Z2 symmetry that you gauge by is the one that acts by x goes to minus x on the target space circle. So it's an isometry of the target space. So it's a symmetry of the theory. And then there's 3 isolated theories, somewhat exceptional theories. And those are obtained by going to this self-dual radius. Generically on this branch, the continuous global symmetry is U1 times U1. But it enhances at the self-dual radius to SU2 times SU2. And you can obtain these 3 theories by gauging certain exceptional finite subgroups of SU2 times SU2, the diagonal. So I'll say gauge finite subgroups SU2. And so let me emphasize that these are all the theories that we know of, but as far as I know, there's no proof that this is the complete list. So already at c equals 1, we're on somewhat shaky ground. It would be very nice to prove this, but I have nothing to say about this. But let me just say that it only gets worse when c becomes greater than 1. And I would argue that we don't have any idea, even qualitatively, for what the space of conformal field theories looks like. We have lots and lots of candidates, but we have no idea to what extent they're exhaustive. So let me give you an example of a very coarse question you might ask about the space of theories with c greater than 1 that we don't know the answer to. We don't know whether there is a gap between c equals 1 and the next central charge that's realized by a CFT. We don't know if there's a continuum of theories at c equals 1. We don't know if there's an accumulation point from the right, just like there's an accumulation point to the left. We know basically nothing about this neighborhood, even just beyond c equals 1. So, all right, c greater than 1. Big question marks, and it's not totally clear how to address those questions. Instead of trying to continue to go up the central charge ladder, let me add one more additional qualifier to make the problem a little bit simpler yet, which is now we're going to organize both by the central charge C and another parameter P, which I will now explain what it is. So let me remind you that one of the reasons that 2D rational conformal field theories are very tractable is because they have a very large symmetry algebras. And in some sense, not in some sense, they have infinite dimensional symmetry algebras. So they're called chiral algebras. Those are defined as the space of holomorphic operators in your 2D CFT. So the holomorphic operator is the product of holomorphic operators is holomorphic again, so they form a kind of consistent truncation of the full operator algebra. And In particular, it's typically a good bouncing off point for studying the whole theory. Likewise, you can define a right-moving Carl algebra. It's just all the anti-holomorphic operators in your theory. And in particular, when you have any kind of symmetry structure, what you want to do is you want to decompose the Hilbert space of your theory into irreducible representations of that symmetry. So let me write that decomposition like this. So here, alpha runs over the representations of this big chiral algebra. And so in particular, it becomes useful to study the representation theory of this big symmetry algebra. Because after all, you're going to eventually decompose your Hilbert space into representations of B. So P is what is going to be the number of reps of B. The idea being that when P is small, like P equals 1, the CFT is very close to being entirely determined by its chiral algebra. And when P is large, it's not that close to being determined by its chiral algebra. So there are two cases when there's a finite number of representations. That's what we call a rational theory, rational control field theory. Those are a lot nicer and easier to handle. When P is infinity, that's what's known as an irrational theory. And these are exceedingly hard to come by. We have some examples, but far fewer than we'd like to have. So I'll keep with most studies of 2D CFT and stick to rational theories. Okay, so now let's start over with the classification. In particular, let's fix P to be 1 and walk up the central charge ladder. So when P equals 1, this is what I called earlier a meromorphic theory, meromorphic CFT. The only representation that the chiral algebra has is itself, the adjoint representation. So for these theories, modular invariance constrains the central charge to be a multiple of 8. So central charge 8. Actually, sorry, before I, so in order to tell you what appears in this classification, let me quickly introduce a class of models that will be very useful for everything I have to say from now on. So we'll come back to this in a second. So I need to tell you what an affine Catsmoody algebra is. So the least painful way to introduce what these are is that they are, so the data that specifies them is a Lie algebra G and a positive integer K called the level. And so what this is it is the chiral algebra of a WZW model, WZW CFT. And what a WZW CFT is it is a I'll just write words since the equations won't matter. So it's a sigma model into G, where G is the simply connected Lie group of little g. Okay, that on its own is not quite conformal, but you can repair conformal invariance by introducing this so-called Wess-Amino term, and that depends on this level. So that's where the level gets introduced. There's an integer number of ways to make this thing conformal. Okay, so the way I've introduced these Kac-Moody algebras makes it seem as though they only arise in this very particular model, this WZW model, but that's not true. They're universal entries in the chiral algebras of CFTs because any theory with G global symmetry has a Kac-Moody algebra inside of its chiral algebra. The reason is basically whenever you have a continuous symmetry, we know by Noether's theorem that there's dimension 1 conserved currents. And those conserved currents satisfy some current algebra. This is, I could have called it current algebra instead. And that algebra turns out to be universal, and it's what we call this Kac-Moody algebra.
Sorry, I have a question. So dimension 1 operators do not correspond to the symmetry operators?
Sorry?
So dimension 1 operators.
They're the no other currents of continuous global symmetries, yeah. In 2 dimensions. Yeah. Okay. Okay, now that I've told you this, we can go back to the P equals 1 classification. So as I said, central charge has to be a multiple of 8. When C equals 8, the only theory is the current algebra based off of the Lie algebra E8 with its level at 1. When C equals 16, of course, you can always just take a tensor product of the theory that you had at C equals 8. It's a little boring, but there's also a new theory. So what this plus means is that you take the target instead of being SO32 to be SO32 mod Z2, but it's not terribly important. When C equals 24, there are 71 theories. And they are completely specified by specifying a Lie algebra, which describes their global symmetries. Complete, oh my gosh. Specified by global symmetry algebra. For example, when the algebra is trivial, there's this famous monster CFT, which has no continuous global symmetries, but it has an action of this exceptional finite simple group called the monster group on it. Actually, for full transparency, I should say this is the only, so this case is the only one that has not been rigorously classified. The rest have. But none of our results are going to rely on this, on the monster CFT being the unique theory without any global symmetries. There are 24 chiral boson theories. These are theories based off of lattices. Even unimodular lattices. And then if you'd like, the rest of the theories can be obtained from actually just one theory by performing different kinds of normal folds. So rest obtained, say, from the and a leech. This is a particular case of one of these 24 chiral boson theories associated to the Leech lattice. The Leech lattice is this funky lattice that solves the sphere packing problem in 24 dimensions. So you can obtain the rest by taking different orbifolds of the Leech lattice theory. Okay, and you might think that we're in pretty good shape. Made it all the way up to 24, but your luck runs out at 24. The next case, it's known from this formula due to mathematicians called the Siegel-Minkowski-Smith mass formula, that there are more than a billion, in fact, more than a billion lattice theories alone, more than a billion chiral boson theories alone. And I'll just point out that over here, only 24 out of the 71 were chiral boson theories. So there may be 2 billion or 3 billion or 10 billion Siegel's 32 theories altogether. So it seems not very promising to try to obtain any kind of explicit classification of Siegel's 32. But the next thing that you might try to do is the next simplest case, which is p equals 2. So
those secret two series are just people one theory.
yes, yeah. Yeah, C equals 32, P equals 1 theories, there's already more than a billion. Somewhat surprisingly. Sorry?
Who wrote them?
So Siegel, Minkowski, Smith, I think, are the people the formula is attributed to, but they were trying to count even unimodular lattices. They weren't really thinking about CFT necessarily, I don't think. But that result has implications for CFTs. In particular, they were able to compute
They have overlapping partition function, I mean J, or and for given J there are many different series, or they all different?
yes, yeah, many theories have the same partition function for sure. Actually, the average partition function is the I'm risking writing something incorrect, but it's like E4 over eta to the 30. Oh, sorry, no. Need 16 here. So it's basically an Eisenstein series over eta to the 32. And with some coefficient, which is calculable. So in some sense, you know the average partition function, amazingly. Where you have to weight by the size of the automorphism group. Incidentally, this has an interpretation in terms of disorder averaging in holography, which is one of the things I mentioned earlier, but it's not the point of today. Right, so for P equals 2 theories, historically, people have made heavy use of modular covariance. So modular covariance is the statement that if you look at the essentially the characters or the partition functions of the different representations and study how they transform under modular transformations, they transform into each other under a representation of SL2Z. So if I define chi to be the trace in the ith representation, this is kind of like the energy up here. Then in an RCFT, what you have is that they transform into each other under a representation of SL2Z. And this places very strong constraints on the spectrum of CFTs. because there just aren't that many functions which satisfy these and other properties. Also, you usually use as input that the representation theory of SL2Z is sort of under good control if P is sufficiently small. So let me give you an example of how you could leverage this to classify theories. So let's ask, what are all the theories with central charge equal to 1 and 2 primary operators? Well, there's a unique representation of SL2Z that's compatible with this central charge. By compatibility, I mean, so this T matrix knows about the central charge because it appears over here. So there's only one SL2Z representation that fits with it. And that SL2Z representation only has a single function with central charge 1 that could correspond to a CFT with central charge 1. So in the vacuum sector, it looks like this, unique vacuum. I'll explain the 3 in a minute. And then the other character is 2Q. Okay, so this is already a pretty strong statement. Any theory with central charge 1 has to have this as its spectrum. But by supplementing this with CFT arguments, you can say exactly what that theory is. So there could in principle have been multiple, but it will turn out that there's only one. And the way to prove that is the following. So we look at this 3 here. This is sort of the number of dimension 1 operators in the theory. And as I described earlier, dimension 1 operators, you interpret them as Noether currents corresponding to some continuous global symmetry. So in other words, 3 is the dimension of the global symmetry algebra. And there are only two reductive algebras with dimension 3, and those are U1 cubed and SU2. So let's consider this case first. Could a theory at the central charge have global symmetry U1 cubed? Well, it turns out that each U1 contributes at least central charge 1. So this would imply that, the reason for that is that it turns out that you can bosonize U1 currents. So you have at least 3 sort of free bosons in the spectrum, and free bosons have central charge 1. So theory that you would get with this should have at least central charge 3. And in particular, that's already larger than central charge equals to 1. You can't add additional degrees of freedom to the negative central charge because we're in a unitary theory. So this is excluded using that very basic reasoning. However, for SU2, so this tells you the global symmetry algebra, but not what level it's at. So we have to decide what level it could be at. Well, the central charge of SU2 at level k is 3k over k plus 2. And in particular, this is greater than 1 if k is greater than 1. So that leaves only k equals 1 as the only viable option. Matches the central charge perfectly. And using just a little bit more thinking, you can prove that then this implies that SU2 at level 1, or as I was calling it earlier, A11, which is one of these MMS theories, is the unique theory with central charge 1. And you can.
But you first need to prove that that's the unique character.
Yeah, you have to prove that this is a unique character, but that's easy to do. So the way that you do that is that so it has to have central charge equal to 1. So the vacuum character has to start as -1 over 24 plus positive guys. The other character H can't be negative, so it has to start at 5/24 or later. So essentially, the unique pole has to be in the vacuum and it has to have strength -1/24 with coefficient 1. Now you ask, is there any other function with those same properties? Let's call it chi prime. Well, if there was, then you could take the difference of chi and chi prime, and that would have no poles at all. So that would be a weight 0 holomorphic modular form. That transforms under this SL2Z representation, and none such forms exist. This is sort of an analog of the statement that if you just look at ordinary modular forms, there's no holomorphic modular forms of weight 0. You have to allow them to have poles. So that proves that this is 0, and therefore that chi equals chi prime. So it is the unique character. So using arguments very similar to this, you can classify all theories in the range 0 to 8, and they're precisely these MMS theories that I was telling you about. So they're A11, which we just described, E21, F41, and E71. So this is great, but there are some shortcomings to these kinds of arguments that rely on character theoretic methods. So shortcomings. So one is that, as was alluded to earlier, I'll just say there exist isospectral theories. So there are pairs of theories which have the same characters. And if you just look at characters, then you can't always, you're sort of blind to that. So an example that we already ran into was the two meromorphic theories at central charge 16. These are isospectral. The second is that not all characters are even realized. By a CFT. So for example, we call Z the partition function of the monster CFT. Sort of famously has a Q extension that goes like this. Oh, 8.1, yeah. Z of tau plus n for any positive integer n is a perfectly healthy looking partition function. It's positive, it's modular invariant, all that good stuff. But we know that there are only finitely many theories with central charge 24. So infinitely many of these healthy looking characters don't correspond to any theory at all. So you need additional arguments to tell you when there's a theory and when there's not corresponding to a character. Another shortcoming is that a lot of the studies that have been done make use of modular linear differential equations to construct characters. And those MLDEs are kind of unwieldy unless you make some simplifying assumptions. So for the experts, what I mean is that typically you have to take the Wronskian index of the MLD to be small. And physically that corresponds to the statement that the sum of the dimensions of the primary operators has to be sort of as large as it possibly can be given its central charge, which you might call as extremal. So in particular, making these simplifying assumptions kind of restricts you to a very non-generic sublocus of theory space. And as we'll see later, most theories that we'll find in our classification are invisible to MLDs with low Wronskian index. I think that's all the shortcomings. Oh, so I ran through an argument that goes beyond just looking at characters. It sort of supplements with some CFT technology, but those arguments that I gave stop working when the central charge becomes even slightly larger than 8. It stops working very quickly. So we need some new tools to bring to bear on this problem. And so I'm going to describe those tools for you. And I'll restrict attention to, I'll illustrate these tools in the context of theories with p equals 2, but everything I say will be more general. But I don't want to, it'll complicate the notation if I try and be more general right now. So let me reorganize the classification one more time. I'm going to organize by the genus. So this is central charge again. This, I'm going to say some scary words. This is the associated unitary modular tensor category. But you don't need to know anything about what that means for this talk. The only thing that you need to know is that it encodes things like the S matrix, the conformal dimensions of the primary operators modulo 1, the central charge modulo 8, fusion rules, and so on and so forth. So it's sort of aware of very coarse information about the CFT. But as we'll see, it'll be very useful to organize theories by their central charge and their associated category. If this means nothing to you, just replace this in your head with modular representation instead of category, and you won't lose much. So one of the reasons that this is a sensible thing to do is this conjecture that every genus has finitely many CFTs. And our results are going to be consistent with that conjecture. So let me describe to you how to classify theories in a given genus under in suitable conditions. So this will be the meat of the talk. So fix some seed theory B in some genus. This needs to be given to you by God, but if you have this, then you will be in business. So first claim is what I'll call gluing principle. So any theory in a quote unquote complementary genus. So at the level of this this data here, a complementary genus has a complex conjugated S matrix. The conformal dimensions of the primaries are sort of inverted in this way, and so on and so forth. Again, if you don't know about UMTCs, just think I'm complex conjugating the SL2Z representation. So any theory in this genus can be glued to V to obtain. So the gluing will look like this. Claim is that this is a p equals 1 theory, a meromorphic theory, with central charge equal to the sum of the two theories that you're gluing. And so in particular, if this central charge is less than or equal to 24, then it should appear in one of those lists that I wrote for you earlier. Namely, it's one of those 71 meromorphic theories with central charge 24, or it's E8 or E8 times E8 or D16 plus. Okay. It turns out you can also reconstruct V twiddle from A and knowledge of how V embeds into A. So from A and the embedding of V into A, you can obtain V twiddle as a coset, which I'll just say in words is the operators in A that commute with V.
So this gluing is like a mathematical way of taking coset, referring to one characteristic.
Yeah, it's sort of a way of relating higher P's to P equals 1, if you'd like.
But you can also consider like P larger than 1 on the left hand side.
Yeah, you can. Yes, indeed, you certainly can. That's a natural generalization of this, but because we're trying, yeah, the goal will be to relate P greater than 1 to P equals 1, where a lot of stuff is known, and that will sort of make this whole thing tick. You know this as like these bilinear relations or whatever. So that's kind of the statement at the level of characters. This is like the CFT statement of what's happening. So what this means is that any theory that exists in this genus, I can first glue it to V to obtain an A, and then I can reconstruct it from A by taking a coset by V. So in particular, this implies any theory twiddle in this genus is a coset of the form A mod B, where A is again a meromorphic theory and B is this theory that was given to you by God. So this is particularly powerful when V is a Kac-Moody algebra. Because when V is a Kac-Moody algebra, it's very easy to take cosets. You just have to understand how to embed Lie algebras into one another. And that's very straightforward. So let me do an example.
So actually, yeah, I have a small question.
Yeah.
So the statement is that for any given V, like it's a factor algebra of A, they always exist, but a unique one or maybe not unique, like a V factorial.
Yeah, yeah, exactly. So there might be multiple inequivalent ways of embedding V into A, and those in principle will lead to different cosets. So that's part of this game, is you have to figure out all the different ways of embedding V into all the different meromorphic theories. But as I said, that becomes reduced to a problem of understanding Lie algebra embeddings, and that's a very classical problem, and it's been sort of solved already. Right, so let me give you an example. So this is the first place where you find a new theory. Good. So let's look at the genus 66/5 mod Fibonacci conjugate. Fibonacci is the category of G21. So what this gluing principle tells you is that any such theory should be a coset of a meromorphic theory with C equals 16 by a theory in this Fibonacci category. So we'll take that to be G2 level 1, which is basically fixed for you. It's the unique one. So there are two options for A. This could be E8 times E8, This case is a little boring because it turns out when you take this coset, then you get E8 at level 1, tensor at 4 at level 1. So you'll recall that this was already one of those MMS theories that we had classified. You can always obtain a new theory by just trivially tensoring E8 with it. So this is a little bit of a boring example. However, you can get a new example by considering the coset of D16 by G2 at level 1. There's a unique way to embed G2 at level 1 into D16 at level 1. And it leads to something which you can write as an extension B12 at level 1 by a tensor with the tricriticalizing model. Some coefficients here. So this B12 you get as the centralizer of G2 inside of D16. The coset always inherits the centralizer as its global symmetry group. But this alone isn't enough to fully account for the central charge 66/5. There's a deficit, and that deficit is precisely equal to 7/10. And there's a unique theory with central charge 7/10, which is the tricriticalizing model by the classification of minimal models. So we know that it has to be the thing which appears here. This is the first example of a new theory, and it turns out that these two theories are all the theories in this genus.
But that the theory on the right hand side has more than 2 characters.
No, it doesn't. What just the trivial tensor product, it has many characters, but when you do this extension, the number of characters get reduced.
So you choose like an IJ such that you have.
Yeah, you choose an Nij such that this bigger thing has 2 characters only, 2 primaries. Yeah.
In terms of two primaries, each of characters is the same as E8 plus F4, right? Because
Yeah.
product is again the same sequence. Then how do you distinguish them? Because they have 2 characters, they have the same.
Yeah, good. You distinguish them because they have different global symmetry groups. This one has E8 times F4 as its global symmetry group, and this one has B12 as its global symmetry group. So you immediately know that they're different just by looking at their global symmetries.
But this could be less.
Sorry?
So P12 is bigger, but they have the same name, right?
Oh, it doesn't enhance because it already,
Right,
these
yeah.
have the same dimension.
Right.
And, right, so it's true that in this case, there's a unique character here, but when you go to central charge greater than 16, there's no longer a unique character. You have some freedom. So I don't want to, so maybe what I'll do is I'll just conclude here since I've run out of time
You
unless
have like 5 or 10 more.
5 or 10 more minutes, okay. So the camera can't see it. Yeah,
So
okay.
I have to go to other one.
Yeah, no problem. So the camera can't see this, but this is a complete list of all the genuses with central charge between 0 and 24. And it describes what cosets you have to take to evaluate those genuses. So the details won't be important, but just to show you what it sort of takes. And when you carefully walk through all the genuses, by the way, how do we know what all the genuses are? Genera? Well, it turns out that UMTCs of rank 2, actually of rank even up to 4, have been classified. So you can enumerate all the genera and take the corresponding cosets. It's a very painful process, but at the end of it all, you find 123 theories, most of which are new. And for this class of theories, we found that all of them could be obtained by gluing together Kac-Moody algebras and minimal models. And also, most of these have Wronskian index greater than 6. So most of them don't satisfy the typical assumptions that people who use MLDs use. So in a sense, MLDs would have been blind to these theories. Okay, so let me highlight some future directions. So the first future direction is the next central charge, which is inaccessible by our methods, is C equals 25. It'd be interesting to know how hard this is. By this gluing principle sort of philosophy, the space of these theories is the same as the space of it's in one-to-one correspondence with C equals 32 theories. Sorry, not quite one-to-one, but it's roughly as complex as C equals 32 theories with an E7 symmetry. So you have to take C equals 32 cosetted by E7 to get these guys. So as I explained, C equals 32 is very difficult. It's more than a billion. But C equals 32, where you impose an E7 symmetry, I'm not sure how difficult that is. One reason you might care is that the functions that could serve as characters of theories at this central charge are functions that arise in a subject called penumbral moonshine. So again, this is about, moonshine is about relationships between modular forms and exceptional finite groups. And so there's a chance that if you do this classification, you'll find a cute theory with relationships to exceptional finite groups. The next obvious direction is to try to classify 3 and 4 primary theories. One of the reasons you might actually be motivated to do this is that by well understood relationships between fermionic and bosonic theories, bosonization, I might be abusing these words by calling it this, but anyways, there's the point is there's a relationship between chiral fermion theories and theories with p equals 3 and 4. And so a corollary of being able to classify 3 and 4 character theories in whatever range of central charge that you're able to do so is that you would have also classified corollary. Chiral fermion theories. I think this would be a very interesting direction. I'm working on it at the moment. Another direction is that I mentioned earlier that we work with these sort of gluing decompositions. So it turns out that whenever you have such a decomposition of A, it implies that A has some non-invertible global symmetries, generalized topological line defects. In particular, the Berlin lines, so-called Berlin lines of V, will act on A by global symmetries. And so, in particular, a corollary of our classification program is a sort of enumeration of the different kinds of non-invertible symmetries that various meromorphic theories have. And I'm writing about that a little later. As I mentioned, it's an open question to show that every conformal field theory genus has a finite number of theories. It'd be interesting to prove this, but because modular form technology is so much more sophisticated than CFT technology, you might try to prove a weaker statement as a warm-up, which I might call spectral finiteness conjecture. Says that there are a finite number of characters in each genus. So a finite number of admissible spectra in each genus. If you prove this and you also prove that there's only a finite number of theories which are isospectral to one another, then you will have proved the entire conjecture. I have two more open questions and I'll finish. Actually, maybe I'll skip that one. Just jump to the most ambitious one. So the most ambitious is, so our philosophy has been that you can relate the classification of P greater than 1 theories to the classification of P equals to 1 theories. And so in particular, this kind of privileges the P equals 1 theories as being sort of extra important to understand because all P greater than 1 theories in some sense flow from them. And so earlier I was a bit pessimistic about the possibility of going beyond central charge 24, but really anything, no matter how coarse that you can say about theory space would be really quite interesting. And so there's I won't quite dignify this by calling it a conjecture, it's more like a hope, but I think it has some good evidence that supports it. The hope is that any pair of meromorphic theories with the same central charge are related by gauging a generalized global symmetry, i.e. non-invertible in general. What's the evidence? So yeah, this seems like an incredibly strong claim to make. In particular, this would imply that all I have to do is take tensor products of E8 and then gauge E8 to some power, and I can reach everything. So the evidence to support this is one that it's provably true when both A and A prime are lattice theories. Chiral boson theories. And two, because we know all the theories at C equals 8, 16, and 24, we can just ask whether this conjecture is true there, and it does happen to be true. Any two pair of theories in this range of central charge are related to each other by orbital folding and generalized symmetry. This would be, I think, maybe the most interesting thing to prove, but of course it's also the most difficult. The only thing I could think to try is to try to see if the proof in the case of lattice theories in some way generalizes to the more general case. Okay, so I think I'll stop there. Thank you.
So thank you, President, for a very interesting talk. Are there any questions from the audience?
I have two questions.
Yeah.
In the beginning, you mentioned the compact unit for CFTs.
Yeah.
And expand compact.
Oh, yeah. Compact just means discrete spectrum.
If
So,
you
like-
release this condition, what the classification change?
Yeah. For example, there's Louisville theory. Has a continuous spectrum. It can have you can tune its central charge to almost whatever you want.
What is the relation between compact and rational?
Good. I think rational, at least my definition of rational, it implies compact because there's a finite number of primaries and everything is an integer conformal dimension descendant of it. It's displaced from the finite number of primaries by an integer conformal dimension. So I think rational implies compact. Compact does not imply rational. They're irrational but compact theories. For example, C equals 1 free boson theories at an irrational value of the radius. Those are compact theories, but they're irrational. Sigma models into Calabi-Yau target spaces, when the Calabi-Yau is compact, are also compact. So on and so forth.
And the sequence 16 theory, a model the F4 level 1, there are 1 theory or 2 theory?
Good. I think one theory. I think you can only, it's just E8 times G2.
Why?
Because I think you can't, I should double check before I make any very strong claims, but I think you cannot embed F4 into D16. You can only embed A1 and G2.
No. Yeah, I noticed your paper says so, but I feel because F4 can embed it in SO26, right?
Good. So the embedding index has to be, good. So I didn't mention this, but you don't need just any old embedding. You need an embedding with special properties because what you need is for the levels to work out. So you're not just embedding F4 into D16, you're embedding F4 into D16 such that it has level 1. And if I translate that into a statement just about ordinary Lie algebras, it corresponds to the statement that we require the embedding index to be equal to 1 if, let me make a more general statement. If the embedding index is x, then in general, this defines an embedding of F4 at level kx into D16 at level k. So in other words, the embedding index tells you how much larger the level is of the thing that's being embedded when compared to the thing that it's being embedded into. So because this has to be 1, this has to be 1, and x has to be equal to 1. So I think we can't use the embedding you mentioned because it has embedding index greater than 1. So it doesn't lead to an embedding like this.
So you need conformal embedding, right?
It doesn't need to be conformal, no. Conformal embedding means the central charges match. But the central charges don't need to match. It just needs to sort of respect the levels of the things being embedded.
Okay.
Yeah. And that's completely captured by this notion of embedding index. Yeah.
So are there any questions? Now let's thank Brendan again. So by the way, we have a dinner tonight so we can get together on the first floor, on the ground floor at 6. Yeah, if you want to, please welcome everyone to join.